test engineering department. Use Python for test control software, data analysis and processing. And Matplotlib is part of what I use whenever I need to generate plots for whatever it may be. So I'll skip the Python evangelism, but I like to use the right language. Python's about the closest it comes to one language to rule them all, I think. And I use it as part of the stack, right? If you need to push down for performance, drop down to C, C++, or whatever, you might go up to the domain-specific language. But if anybody has any questions about should I use Python or anything like that, talk to me later on. We'll talk about that. I have strong feelings about that. So the documentation at matplotlib.org is very, very good. So this will be mostly demonstration. There's a few pages on there, great places to look that I always start out when I'm looking for something if I need to visualize something in some way. There's a gallery with code examples as well as the shots, the different plotting examples. There's a plotting commands summary, which is useful to, I know I need to do this, but I don't remember what the command is for that. There's the examples, and for the interactive rendered plot, there's some navigation keyboard shortcuts too that might be useful. NumPy, SciPy, IPython. NumPy is the numerical processing toolkit. How many people have used Matlab? Out of curiosity. Oh wow, quite a few. Okay, so if you've looked at NumPy or SciPy or Matplotlib, you'll see definitely some overlap there, but at least now you're using Python, and definitely a huge improvement there, I believe. Matplotlib utilizes NumPy at the very least, and IPython, I'm reminded I should start using IPython, so, and again today, so definitely a useful shell environment to take a look at. And of course there's alternatives. If you need to throw something up real quick, OpenOffice Calc, Excel, sometimes you just have a little bit of data to throw up to display. There's Matplotlib's pretty much a 2D plotting library. There's other visualization toolkits that are available. If it doesn't do what you need, there are alternatives to take a look at as well. So use of importing and using Matplotlib, you can import it. We'll take a look at some examples of those, but you can also do a from PyLab import star, which will import all sorts of NumPy, SciPy, and Matplotlib stuff into your current namespace, and then it's kind of like having a MATLAB environment where you have all these commands just right there in the shell environment. So that's kind of PyLab. You can fire up IPython and have it automatically. Earlier examples of that today, and use it some other ways. We'll take a look at some examples of that. There's different what they call backends for Matplotlib, so it'll throw up an interactive, while using it interactively, it'll throw up a plot of that. Or you can create raster vector file formats like PNGs, PostScript files, which I've used sometimes. We'll show an example of that. You can generate PDFs too with multiple plots, but there's some pros and cons to that. And there's some GUI do widgets with Matplotlib type plotting. I haven't used those. If you need to, it's definitely, you can take a look and see if there's something there that you can use. I'm going to show some examples with that S&P data that we saw earlier today, and I'm going to show a couple of other examples. Somebody asked about two-scale plotting earlier today too, and we're going to show an example of that. And then I'll show some real-world examples of stuff I've done with Matplotlib. So again, it's there, it's quick and easy, and knock out stuff real quick and get it done with Matplotlib just like we do with Python. So I'm going to do, it's not as pretty as IPython, is it? But I'm going to copy and paste code and invoke it from this running Python interpreter here. So you can see that large number. That's it. Okay. In this case, I'm not going to import everything into the namespace. So I'm going to import the PyPlot portion of this and as PLT, just like people often do NP. I'm going to import this one for a utility function we're going to use. Just this CSV to record utility function, and this we'll use, this PDF pages we'll use later on when I demonstrate that. So copy that. I should use a better shell too. So the first thing I'm going to do is read in the historical closes file that was circulated before this workshop. And this is kind of interesting. They, before, when they shared this data set to use, I had recalled seeing something that could read in a file, but I had not used this before. So it's actually kind of interesting. This record data structure. You can see it imported that CSV file, and to see if it converted the time column to data types, and it also has the columns of that tabular data are available through names as well as through indexing. So we can do x dot open, for example, to examine that, so we can see the opening price column, or the opening S&P average column. We can see that. So this data, we can go ahead and plot it. So we'll just use the plotting function. And I'm just going to plot price versus the date. This formatting statement, again, if you check the plot documentation, it's going to plot this as points. You can also specify color, plot as lines. You can put all kinds of different tick mark shapes. Go ahead and show that. And so we can see we've got that data from the CSV file. What was that? I should show that again. So, and this is the interactive backend, so I can go ahead and resize this. If you just have some quick data to take a look at and examine, it's kind of interesting. You can get in, you can zoom, you can pan around, you can zoom in on some point, scale it, whatever. You can also save that off as a PNG image, for example. So if you're just doing something real quick, interactive from a normal Python shell that you've imported PyLab, or from IPython, you can go ahead and bring up your interactive plot, get what you want, save it off, and share it with somebody. So I'm going to go ahead and plot, in this case we're going to plot two things. The opening prices, plot as points, we're going to give it a label, open. We'll also plot the closing prices and label that as close. And this extra command legend is going to put a legend up, so I'll get these two plots will be color coded automatically, and then the legend will show me which color traces for what information. So not very interesting, because the open price and the close to each other, so with the resolution of the screen I don't really distinguish the two colors, but the opening prices are plotted in blue and the closing are plotted in green. So we'll go ahead and let's see. We'll show a way of plotting that in a couple of examples, so you can see both of those. But again, not very interesting. So I'd like to take a look at the range, so that the column of prices and low prices for the day are vectors, so I can go ahead and do a vector subtract, and what I'll get is a vector values, that's the ranges for each day. You go ahead and plot that over the days. That might be a little bit more interesting to look at. So this shows me how much the prices are changing over the course of the day. Of course, when I look at this, I automatically see that the range through the course of the day for the first few years looks very data file. I see that there's actually no information there for that. So, but otherwise, I see things got pretty active around the .com era and spiked up again and such. So. But since those are absolute ranges, that's also not very fair to look at it that way. So what I did here is create a daily range and scale each day's range versus the closing price and multiply by relatively. We can look at, say, the data from the 70s and compare it to the 2000s and get something a little more comparative. And we can see some flurries of activity here at certain dates that were quite busy. That 87 market crash was interesting, for example. So sometimes I want to show more than one piece of information. Use subplots, and the subplot command, this is interesting. It first number is the, you can also, instead of just a single number here, I can say 6, 1, 1, but the first number is the number of subplots, and then this is the column, and then the row, so you can have a tabular arrangement of multiple subplots. I'm going to go ahead and plot the opening, high, low, close, volume, and the relative range. So probably I should take these charts out, or I could label these. I could label over here on the side, put open, high, low, close, instead of using this legend. I think that would be better in this case. But you can see quite quickly visualize a bunch of different data on the plot. So maybe I hate to copy and paste code and have something repeated that's almost the same. And here I've got the same thing repeated: plot, legend, subplot, plot, legend. A little more Pythonic would be to iterate across a list of things and do that subplot, plot, and legend. So this code is a lot more compact and what I prefer to generate, I think, usually, depending how fast I'm moving and getting something done. So it's a bit more of a Pythonic way to do that. And again, that's just by, so from our iter tools, enumerate. Or that's not even from iter tools, it's built into the default namespace. So, every time I do these various plotting commands, create a legend, create a subplot, plot a trace of data, I don't see anything until I issue the show. So turn on a more interactive mode of plotting. And right now we're not in an interactive mode, so I'll go ahead and turn that on. So this will turn on interactive plotting. So I'll do a subplot, and that shows up. I can right away, and now I'm going to plot another subplot. And that showed up right away as well. So you can do, if you're just working really interactively with some data, you can go ahead and plot it, change things, put some additional data, if that's useful. Turn that back off now. Okay. This I find pretty useful too, is being able to plot directly to an image file instead of interactively, especially if I'm doing batch processing on a bunch of data. And we'll show from a workplace example that later on. But in this case, I'm going to go ahead and do all the normal plotting commands. So plot the data, put a title, put a label on the x-axis, put a label on the y-axis. And then instead of show, I'm going to do save figure, and I'm going to specify the file name. And let's see. So it saved the that as a PNG image. But I can also still show that in the interactive environment as well. Let's see.
You said it does vector graphics. Will it do like SVG files as well?
Let's take a look at that. I haven't used SVG from this, but let's see. It looks like they have SVG. Yeah.
But it can still be coming out as a bit.
At least the PostScript files are relatively huge, so I think if you, it may be that in the vector format someone could extract back out your raw data if that's a concern.
Why don't you try saving it and zoom it out and see if it's actually doing it.
SVG format?
Yeah.
So, it's 16,000 lines, so it's
Yeah, it's the exact points that you want to.
right. So and PDF's the same, so it's not very compact. I think if you have a large data set that you're doing that. So depending on what you want to do, I might want to rasterize that first and put it in that format. Depends on what you need.
Yeah, one of the save commands you can have DPI equals such and such. I think it has default like 100 DPI. You might want to do 200 DPI or higher if you want to go zoom in on it.
Yeah, I haven't looked at that, so but because I haven't really used the vector format file save stuff, so I haven't looked at that trade-off. So. Okay. So I did try this just because it was in there. And this code here will create this PDF pages object, specify a file name, and then I'm going to iterate through these various sets of data, plot them with the title and legend, save the figure and close that. And that should create a PDF file with multiple pages. This file size is rather large. From what we saw when we looked at that SVG, it's the same thing. It's putting in pretty much all that data. Those data points. And you can see by the drawing time, you can see that it's a lot of vector data in that, right? So. If I had a relatively lean set of data that I was rendering, or if I pre-process it first so it was fairly lean, then it might be useful. But there's another library, I think Report-Lab, which might be useful for creating multiple plot data reports and PDF documents. I might start looking at something like that too if I need to do very much. I don't know if I would use this myself. If I had a plot and I wanted to annotate it, I would probably just open it up in GIMP or something like that and touch it up real quick. But you can annotate within Matplotlib. So in this case, plotting the daily range, I locate the peak by looking at that daily range data and finding the maximum value in that. So I find the point where that maximum point is in that data. And then use this annotate function to put some text in there and with an arrow. So you can actually put in the, so here's the actual data point. So I'll zoom in on that a little bit. Somebody mentioned the clipping thing the other day, or earlier today too. So this is the example I've seen of that. So that might be a little bit of a glitch, I think. So there's actually a data point there that's been annotated. There's an option to change the value, so the head of that arrow will be off by maybe 10 pixels, or however many pixels you want to be, so that it's a little bit easier to read. So that's just some basic Matplotlib type plotting. I've got another example I want to show. Okay, in this example, I'm going to create just two data series. I'm going to plot those in one single subplot, so they're going to be overlaid on top of each other. One of them I'll plot with red, the other one I'll plot as blue, and let's see. This twin x function lets you plot two series and have two different scales for the y-axis, vertical axis. So that's so in this case, the range for red is from 1 to 6, and the range for blue is from 0 to 3. So I've got more than one scale here for the vertical axis. Both of these were auto-scaled, and sometimes I don't like to look at different data with auto-scaling on, because then it's hard to see the differences. I think it's better to visualize or to see what the information if it's not auto-scaled. So the same example's repeated, but in this case the Y range is set from 0 to 10 for both data sets. So at times, so this is fairly common with a lot of the data work I do, is that I actually want to turn off auto scaling because it hides some of this information, I think. So in this case, you can see there's quite a bit of difference between these two sets of brain data.
So if you turn off auto scaling, why have two axes?
Yeah, I guess you could turn that off too in this case. Yeah. When I was putting together the examples, I just put that in there since it came up. But yeah, you could definitely turn one of them off. There's no need to do that in that case for sure. So, okay. Let me show some other examples. So I'm going to show a few examples from my day-to-day work. So I've got, in this case, I'm looking at a digital to analog converter. Is there anybody who doesn't know what a digital to analog converter is? Like what we used to listen to our MP3s and everything? Okay, that's good. So basically, a sequence of numbers are fed to the digital analog converter, and the output voltage will be proportional to that number. So you could have your the string of numbers could represent the music, feed through the DAC, and then feed into a speaker, and then you can listen to your music. So in this case, we had some measurement data. We measured the voltage out from a DAC. We walked through all the possible numbers in the range that is supported, measured the voltage out, and it should be a perfect straight line. There shouldn't be any defects in that if it's a perfect DAC. I had a couple of libraries to look at a DAC transfer function, and in this case, from that transfer function that was measured, went ahead and plotted out the actual transfer function itself, and then also plotted out basically the finite difference. So if you go from code 1 to code 2, you would want the voltage step by, say, maybe 1 millivolt. And then when you go from 2 to 3, you want it to be 1 millivolt higher than that. And from 3 to 4, you want it to be 1 millivolt higher. It should always be the same step size. And if it's any different from that, then that would be a defect. It would be less than perfect. So in this case, I had 4 files for a 4-channel DAC and generated these plots. And this was a student project. So if we look at these 4 plots, so this is the transfer function. And if I don't take the finite difference, if I don't do a derivative, then it looks like a straight line. I can't see these small imperfections. But when I take the derivative here, I can see, well, it's not perfect, is it? And then this also shows the integrated, this value when it's integrated looks like this. So this shows the departure from a straight line. This shows the step-to-step defects. So if I look at these 4 channels, it's a straight line as far as I can see. But this plot here, you can see, you see some spikes in here, right? And it looks different from channel to channel. But you see 4 of these are showing up every time. So when we looked at this student project, we could say, hey, something's going on. And in this case, there was a layout issue on the silicon that created a common defect.
Were you running that in? Were you running that in? Is this part of the Matplotlib, or is that part of Windows?
The plots were generated with this. So I wrote some code, used Matplotlib, and then had the set of input files, which were the raw transfer function data, and generated these PNG plots. So once I open them up with the image viewer, I can just cycle through them by next
I
image
thought you might
file.
be doing real-time plots.
Yeah. So this kind of it's convenient. It's a quick way to review a lot of data. So. And here's another example. In this case, the data files are from a vector network analyzer. So that's a piece of equipment that measures the frequency response of stuff. In this case, it's a measurement circuit. And so as a function of frequency, you can see the gain of that. So if I put a signal in one frequency, what's the amplitude of the signal when it comes out? So I had a set of files of these measurements for a number of boards, and I wanted to look at them and compare them. So with Python, just whip something up real quick. In this case, I did that pylab import star, so brought everything into the namespace. Wrote a small function just to read in those files that were saved by that piece of instrumentation in whatever format that vendor had created. Then I just iterated through the list of those files, read in the data. So the data set is just frequency and amplitude. That's all we care about. It's 2-dimensional data. And then go ahead and plot those and label the plot. So I can take a look at that. And when I was So in this case, when I was done with it, so 5 different implementations of the circuit were measured, and at low frequency, they all look the same. But at a higher frequency, you can see there's some departures from each other. Like this blue one has much more bandwidth than these later ones. So some of them, these 2 stuck together close and then started to depart at higher frequency. In this case, the actual circuit's not important, but it's a nice way to compare these different, the prototype and several boards, or a board measured at a different point on the board made a difference. So it was a quick way for us to review the data that we had, the measurement data on this circuit. And here's another example. In this case, the data is from in this case, this data is for testing an analog to digital converter. So in this case, a sinusoid was fed into an analog to digital converter. It measured the voltages and spat out integer numbers. So in this case, it's, I forget, a couple thousand points. And if I plot that data just as is, I should see a perfect sinusoid. But it's kind of hard to look at that again because it's hard to see details at that large scale. So we want to do a Fourier transform of that so we could look at the spectrum, the spectral content of that. Since we're feeding in a sinusoid, there should only be energy at one frequency, the frequency that sinusoid, it should have only one frequency. If there's any energy at other frequencies, then it shows a defect. So in this case, let's see which one it is I want. So I just wrote a small function to read in that data from the files. Another small function to take that time domain signal and create a spectrum from that. I wrote a small function to create a PNG plot of that spectrum for comparison, so we can compare different measurements. So, since I had a directory full of those data files, it just read in the list of files from that directory, iterated across them. The file name tells me its serial number and the voltage and temperature it was tested at. Read in the data, create the spectrum, do a little bit of math on the spectrum, and plot, save that out as a file, the plot, and also save off some data in a CSV file as well. So here we can see the tone. That's the axis down here is frequency. That's 10 megahertz, 20, 30. This is amplitude. There should only be energy at this one frequency because that's what was fed into the analog to digital converter. But we can see second harmonic. So there's some harmonic distortion going on in this analog to digital converter. So that'd be like a THD specification for your stereo gear. I can skim through these plots real quick. And this is interesting because it's the same part number 10, and it should be fine in both cases, but I see that the fundamental amplitude is severely reduced in this case. And not only that, but these higher order harmonics have popped up quite a bit. So something was going on there. To me, I think that was a test repeatability issue. I think they were collecting the data by hand and had some issue going on with that. But basically, I was able to write this Python code real quick. Somebody had this raw data, said, we need to look at it. Wrote some code, generated plots, skimmed through here. I could see right away they had a test repeatability problem that they needed to address. So those are some examples that I had. Does anybody have any questions?
Not much. This is a lot like what I was doing just a few months ago. I really like the interactive plotting and scroll around and all that stuff, and the boss saw me doing that and thought, oh, that's pretty cool. When I saved PNG files, pass those on and put those in for you. There's no way for someone else to later come back and get that plot interactively and zoom in and all that. It's like they're thinking of an easy way to let them do things like that.
You save a transcript, I guess, of what you did, or?
I save the Python code, but I can't give it to them because they don't know Python.
That's actually why I asked about the SVG file, because if you pass that around, depending on what you open it with, you can actually scroll in and zoom in and everything, because it is a vector graphic. And then Internet Explorer, there's some things you can do with that too.
If I render that raster PNG file, I can zoom in, but what's going to look like is coarse blocks, right? But if it's the SVG, I can zoom in until I can see the granularity of my data, right? Which it will be limiting as well. So.
Yeah, but on a big plot that can be too slow, so I've ended up doing just decrease the dots per inch.
Right.
Plot function, value 200 or 300.
Whatever's reasonable for the
I get huge
application.
with 300, so double them to 200. The other thing you didn't quite mention is you can do histogram plots.
Yes. Now, is that part of Matplotlib or Numpy or SciPy?
Slightly different arguments to the command, or to the plot command.
The histogram plot I use a lot too, the histogram function. Quick question, who's tried to do a histogram plot in Excel? Yeah, it wasn't pretty, was it? I didn't think it was. Anyway, but yeah, the histogram plots are useful too. And Also, the NumPy and SciPy have a lot of statistical processing too. So all the normal sorts of things, standard deviation, mean, those sorts of things I use quite a bit too. So to get statistical metrics on data sets.
What was that you were using for doing real spectra?
Just the Fourier transform from SciPy and NumPy.
Yeah, but you had it hidden in your own.
What was it?
You had it hidden in your own function, real spectra.
Oh yeah, I think we can take a look at that offline. I think.
But well, okay, I'll ask.
Yeah, you've looked at the FFT library, right? So it's just.
Well, I was also, there's a Matplotlib has a lot of stuff thrown into it.
Right.
One of the strange things it has on it in there, it can do cross spectra of a set of data you give it, and the power spectra all at once.
Okay.
Just give it a bunch of blocks of data.
Yeah, I looked up the first one that met my needs and tweaked it a little bit. We can look at that. We can look at that code if you want to offline. That's fine. Yes.
Can you get bar charts, or you have a choice of outputs?
Oh, yeah. Actually, let me bring up. I did preload some of those pages, and I can send out a list of links to these specific things. But again, I'm a utilitarian user. I haven't touched the full breadth and depth of this library, but definitely hit the website. The documentation's pretty decent. A few pages that are useful. The thumbnail gallery, I think, is very interesting. There's some box plots, so we can click on that and take a look. So they'll have examples, and they'll have the code that was used to generate that. So I'd recommend taking a look at those and see if there's something close to what you want to do, and see if it looks too cumbersome or if it looks like a good option for what you want to do. And here's the histogram function. I love that. I use it all the time. So where's the actual feed of that? I have to search for this. There it is. Yeah. So the histogram function's there in the NumPy library. Yeah. Highly recommended if you need to do that. So there's quite a few examples in here. Some of them might be a bit getting a little bit tricky, I think, in terms of it takes a lot of code to generate a particular type of plot, but some of them should be straightforward. I see a lot of bar charts that definitely be worth taking a look at.
There's a spectrum
Yeah. Let's see. Lots of surface plots. So that's the thing. According to the webpage, at least, they're a 2D plotting library. Who knows who this is?
Great
Very good. So they describe their 3D plotting as being experimental, and here's some screenshots of that. I haven't looked at this. I haven't needed to do any 3D plotting recently. So, but they certainly do have some 3D plotting. They do suggest looking at like PyVTK or something like that. There are other visualization libraries available, and if this one doesn't do what you need, take a look and see what you can find. You can ping me offline, and I can maybe point you in one direction or another, depending on your needs. Maybe not. So, yeah.
I should say I had to do some plots with about 10 data sets and lots of extra axes. So if you ever have a need to do 3 or more axes, there's only one way that works in general to do 3 or more. So talk to me afterwards.
So there's so besides that gallery, which again look for something that's close, and there's the sample code that's definitely a good place to hit. There's a plotting command summary. So I know there's a way to mark to label the x-axis, but I don't remember what the command is. So here I can find it. Control F, search, and find label. Labels for contour plots, all kinds of things in here. So this page is also a useful one. This page has examples, and this dives more into the breadth of the library. So I think this could be a useful page to hit to look for. So there's a bar chart demo. Yeah, so it points us back to the same one in this case. And that, I may be tempted to the bar chart one, since it looks like there's a few steps to do that. I'd probably wrap that in a function, and then just to keep my code clean, simple, maintainable. For that interactive environment, there's some shortcut keys for this too. I didn't know this, but you can actually toggle between linear and log plotting. I thought that was kind of interesting. And constrain your zooming to either axis. Full screen might be useful, I don't know.
Can I ask again about the numbers you were using for the subplots?
Oh, yeah, so we can take a look at...
Is each digit significant? Or is it?
Yeah,
it's
let's
kind of confusing
look
how that-
at... So subplot. Let's pull it up. So number of rows, number of columns, and then the specific plot number. So
You were using without the commas, so.
So I had that. I remembered incorrectly. So so if you wanted like a 2x3, you'd say 2, 3, and then you need to tell it which subplot am I working on right now.
Okay, and you
so
give
the
it
last
a-
number would tell.
Give it an arbitrary number?
For a 2x3, it'd have to be 1 through 6, right? Because that 2x3 would have a total of 6 subplots.
Oh, okay, I see.
Right. So you just tell it which one it is that you're working on. So.
You had 3-digit numbers, so I was a bit confused.
Yeah. So one of them was the number of rows, which was 6. Number of columns, which was 1. And then
You
the
didn't
plot
have any
number.
You didn't have any commas with it.
It's the example.
No,
Yeah,
because
you
you
can do it
can do it either way.
Yeah.
So does
So
that-
when you get more than 10, you're gonna do the comma way.
Yeah. I did it both ways.
That's
With
crazy.
one base copy just throws them off, I guess.
Yeah, so they show an example, you know, they show this way of doing it, but they also show the other way of specifying. So we have to see. But yeah, it's a very useful library for quick plotting. Okay.
Thanks to Drew.